explainer and honestly unravel one of the absolute greatest detective stories in all of science, the hidden structure of matter itself. We're going to break down exactly what makes up the physical world and how all those tiny, invisible pieces actually interact with each other. Think of the physical world as this massively complex piece of architecture. Every single thing around you, including your own body and the screen you're looking at right now, it's all constructed from fundamental building blocks. But what exactly are they at their absolute core? And what kind of rules govern how they connect? Well, that is exactly the mystery we're unraveling today. So here's our roadmap for the explainer. We'll kick things off with the basic building blocks, then move into discovering subatomic particles, map out the evolution of atomic models, dive into electronic configuration rules, check out valency and ion formation, and finally decode the mystery of isotopes. Let's get to it. Section 1, the basic building blocks. We're going to start with the macro, the big picture, and just zoom all the way in to the micro. You know, the ancient Indian philosopher Maharishi Kanad actually hit the nail completely on the head centuries ago. He theorized that if you take any piece of matter and just keep dividing it over and over again, you'll eventually reach a point, a particle so incredibly small that it just literally cannot be split anymore. And as we know today, we call this unbreakable fundamental unit the atom. Building on that ancient philosophy, Sir John Dalton came along and proposed his famous atomic theory. He firmly established that atoms are indeed these fundamental, indivisible, pure units of matter that can't be created or destroyed. Plus, he realized atoms of the exact same element are totally identical, while atoms from different elements are, well, entirely different. And crucially, they combine in fixed, simple ratios to find stability. Like water is always strictly 2 hydrogen atoms and 1 oxygen atom, no exceptions. Section 2. Discovering subatomic particles. Now, get ready for a massive plot twist here. What if Dalton was completely wrong about atoms being totally indivisible? Think about it. If atoms were truly these perfectly indivisible, neutral little solid spheres, the whole concept of static electricity just wouldn't exist. Like, remember rubbing a plastic pan on dry hair and then picking up tiny pieces of paper with it? That magnetic-like attraction happens because opposite electrical charges are building up. This simple, everyday phenomenon actually proved that atoms must contain hidden, charged subatomic particles that can literally be shuffled around. To prove this, scientists use these really cool vacuum discharge tubes at super low pressures and high voltages. First, they discovered cathode rays, which were streams of particles shooting toward a positive charge. Since opposites attract, that meant these rays had to be highly negative. Bam! We found electrons. Then, by tweaking the experiment, they spotted anode or canal rays, traveling the opposite way and deflecting toward a negative field. Those were our positively charged protons. So much for the indivisible atom, right? Section 3. Evolution of atomic models. Okay, so now that we actually found the pieces, the protons and electrons, scientists had to figure out how they fit together inside this tiny atom. Tracing this evolution is basically watching a rapid-fire timeline of scientists fixing each other's mistakes. First up, J.J. Thomson. He pictured the atom like a watermelon. You know, a big positive red sphere with little negative electron seeds just embedded all over it. But then, his own student, Ernest Rutherford, comes along and proves that completely wrong, which ultimately led Niels Bohr to map out strict, discrete energy orbits for those electrons. But wait, let's look at exactly how Rutherford shattered Thomson's watermelon model. Rutherford's gold foil experiment was an absolute game changer. He fired positively charged alpha particles at an insanely thin sheet of gold foil. And what happened? Well, most of the particles zipped straight through like absolutely nothing was there. That proved the atom is actually mostly empty space. But here's the crazy part. About 1 in 12,000 particles completely rebounded, just bounced straight back. That meant almost all of an atom's mass and its positive charge had to be jammed into a microscopic, incredibly dense central nucleus. So the huge takeaway here is that an element's entire identity is defined by its atomic number. We represent this with the letter Z. That number is exactly, precisely how many positive protons are sitting right there in that central nucleus. Oh, and a perfectly neutral atom? It's going to have the exact same number of negative electrons flying around outside to balance it all out. Now, since those orbiting electrons weigh practically nothing, I mean, their mass is totally negligible, if you want to know the actual weight of the atom, you really only look at the nucleus. You just take the positively charged protons, add them to the neutral particles, the neutrons, and boom, that combined total gives you the mass number, which we represent with the letter A. Section 4, Electronic Configuration Rules. let's shift gears and look at how those weightless, speedy little electrons behave outside that heavy nucleus, all thanks to some clever rules by Bohr and Bury. So there's this incredibly simple yet totally golden formula, 2n squared. This is literally the ultimate rule for figuring out the absolute maximum number of electrons you can cram into any given atomic shell. And the n here, it simply stands for the energy level as you move outward from the nucleus. Let's actually plug some numbers in and map this out. By using that formula for the energy level n, we can perfectly predict the capacity for the K, L, M, and N shells. That first inner shell, K, is level 1, so 2 times 1 squared means it only holds 2 electrons. The second shell, L, holds up to 8. The third shell, M, holds 18, and that N shell can hold up to a whopping 32 electrons. This whole structured filling system, that's what we call electronic configuration. But here's the thing, beyond just filling capacity, nature absolutely loves stability. Enter the octet rule. This dictates that elements will do pretty much whatever it takes to get exactly 8 electrons in their outermost or valence shell. If they fall short of 8, they get highly reactive. They'll desperately seek to trade or share electrons just to reach that stable 8. Now, little hydrogen is our one major exception here. It only has that first K shell, so it just wants 2 electrons. We call that the duplet rule. Section 5, valency and ion formation. And it's exactly this desperate drive for 8 outer electrons that fuels pretty much all the chemical reactions and bonding we see in the entire universe. So, if you want to find an element's combining capacity, its valency, you just follow 3 quick steps. First, look at the configuration and count those outermost valence electrons. Second, ask yourself, is it easier for this specific atom to just toss away a few extra electrons, or should it try to grab a few from a neighbor to hit that magic number 8? Once they make that trade, they aren't neutral anymore. They transform into a charged ion. Let's look at 2 totally different paths to getting stable. Take sodium. It's got just 1 lonely valence electron. Naturally, it's way easier to just lose that 1 than to somehow scavenge 7 more. So it drops the electron. Now it has more positive protons than negative electrons, making it a positive cation. On the flip side, look at chlorine. It has 7 valence electrons and is practically begging for just 1 more. When it grabs that extra electron, the negatives went out, creating a negative anion. Put this positive sodium and negative chlorine together, bam, you get perfectly stable table salt. Section 6, understanding isotopes. Finally, let's throw a really fascinating curveball into how we understand elements and their mass. Okay, so we established earlier that atoms of the exact same element are supposed to be completely identical, right? Well, mostly. Sometimes, atoms of the exact same element have their normal, defining number of protons, but they secretly carry a few extra neutrons hidden inside the nucleus. We call these heavy little variations isotopes. Let's break down how these isotopes work. First off, they have the exact same number of protons, so their atomic number is unchanged. They are absolutely the same element, but those extra neutrons mean they have a totally different mass. Take carbon. Out in nature, you'll find carbon-12, carbon-13, and carbon-14. Yet, because their proton count is identical, their outer electron configuration is identical too. This means they behave exactly the same in chemical reactions, even though they literally weigh different amounts. And that actually leaves us with a really provocative question to wrap things up. If an element like carbon can naturally exist weighing 12, 13, or even 14 units, how on earth do we decide what official atomic weight gets printed on the periodic table? Do we just pick one, or do we have to average them all out based on how common they are? It's a fundamental puzzle that literally shapes how we measure our entire universe. Thanks so much for joining me on this explainer, and definitely keep that curiosity